So let's start with examples, and as usual, when we learn by examples, we will start from the simple and gradually grow. So let's look at the most common working horse of quantum computation, which is the multi-controlled gate, in this case multi-controlled X. So this is the function. What the user cares about in this particular case is that this function will be implemented. It has 6 control bits and one target bit in this particular case. It can also be controlled on zeros or ones, it doesn't really matter. And this would be a particular implementation of this function. It actually uses no auxiliary qubits. So the same number of qubits in the physical implementation as in the logical description is what the user wants. It has 168 CNOT gates and the depth of 225 in terms of CNOT gates. I believe it is optimized. We cannot do better, as far as I recall. And this is a different implementation of the same function. This would be a 9-qubit master implementation of the same 7-qubit functional multi-control knot. So here you trade off 2 additional auxiliary qubits if you have them for much less CNOT gates. There could be an 11-qubit master implementation, and so on and so forth. And in this particular case, anyone here coming from engineering, one of my other hats, by the way, I have so many hats because I'm just very older than you guys. When you reach my age, you will have at least as much expertise as me. So if we are looking from an engineering perspective, we just have a trade-off table, which is so common in any engineering EDA tooling. And we see that the machinery, that the automation, that the synthesis engine needs to trade off between the widths of the function in any particular point in the algorithm. I did not tell you where this MCX is functionally located in the algorithm. So at any particular point, the synthesis engine needs to trade off between widths, number of available qubits, memory if you like. Actually, the auxiliary qubits, it would be just the same. Usually the code is not tabular, but functional code, which trade-offs between the different parameters. And then the technology will find the optimum, but here I want to stress the point. It will find the optimum, including it has much more degrees of freedom than a regular compiler that you would think about. It can recognize how to add, in this example, auxiliary qubits, even though the user did not specify that auxiliary qubits are part of the game. And I will show other examples where you will start noticing the large design space, the large freedom of choice that the technology has.